Okay, good morning, everyone. Okay, so we are here, okay, with a live panel discussion, okay, on our today's topic, rate of reaction. Here we have 21 chemistry experts from around the world, and all of them have completed their PhD in many areas in chemistry, and they are here to help us out related to our rate of reaction chapter discussion. So let us actually start off. Okay, maybe we start off with asking question to Dr. Justin. Dr. Justin, talking about rate of reaction. What do you think? How do you can you explain to us how we can actually measure rate of reaction? Is there any formula that we can actually follow?
There's a formula. It's the change in amount of reactant or product over time is the formula we can use to get the
Okay, so the formula is going to be you're talking about the changes that happens in the reactant and the product divided by time. Yeah, so that is actually going to give us the rate of reaction. Apart from changes, I think related to changes with reactant and product, is there any other ways to measure rate of reaction? Because I'm quite confused. Because I think a lot of people get confused when we say change in reactant and product. What kind of change are we looking for? Can anyone help us on this? What kind of change?
We could look
We
for the
could
masks and
also use colorimetry, in which we kind of like observe the change in color or change in mass of the precipitate formed or the electrical conductivity of the particle.
Okay, thank you, Dr. Ashley. So Dr. Jonathan wanted to say something. Can we actually continue with Dr. Jonathan?
I was gonna say the same thing. I was also gonna say the color and the electrical conductivity.
Okay,
And
so
also,
talking about the electrical conductivity, how do we measure rate of reaction related to electrical conductivity?
we
Very
could measure
interesting.
the rate of reaction of aqueous solutions by
Okay,
electrical conductivity.
so it means the formation of ions. So they do conduct electricity. So you measure from there. So as Dr. Ashley mentioned about measuring intensity of color, is there any particular device that we use to measure that?
We could use a colorimeter.
Okay. Colorimeter. Okay, good. Okay. Is colorimeter the same as the one that we learned about calorimeter or something like that?
No,
colorimetry
kind of
is
like
not
measures
colorimetry.
calories, and this is measuring the change in color, or as you said, the intensity of color.
Yes, yes. Okay. Okay, now it's clear. Thank you, Dr. Ashley. So so let's actually move on. Yeah. Let's move on. Maybe let's actually discuss. I think there is, when we talk about rate of reaction, we always have this theory, which is collision theory. So maybe Dr. James, would you like to actually enlighten us about what is collision theory? Dr. James, I think technical issue. You're muted, I think.
Have the things when like they react when have the energy, then they like collide with each other like the vertical.
Okay. Anyone else want to actually add in related to this collision?
They also have to have the correct rotation.
It's particle that need to be in the correct orientation and have sufficient energy in order to react.
Okay.
Or have a reaction occur.
So basically, we are looking at when we talk about this collision theory, it means we are talking about reactants. They are colliding with each other. And you mentioned about there are two things that we need to focus, which is one is they collide with the correct orientation. And what is the second one, Dr. Ashley?
Correct orientation and have sufficient energy.
Okay, sufficient energy. Okay, noted. So so if you look at this, the next part is going to be, what are the two indications based on collision theory that speed up the rate of reaction? So are you telling us that the correct orientation and having the enough energy is the two indications to speed up rate of reaction? Dr. Nevan?
Sorry, sir, what was the question?
What are the two indications that actually can say that the rate of reaction can be speed up?
Temperature, catalyst, and
No. That is actually factor. Maybe the indications. Like for example, based on the collision theory, just now Dr. Ashley mentioned about they are colliding with the proper orientation and must have enough energy. So I know that one of the indication is going to be must have adequate energy, which is going to be you need to have more proportion. I think some previously some in the earlier discussion we have. When you have more particles having the proportion greater than activation energy, I think that is important. How about one more indication?
Sure. Can I
The
answer?
frequency of collisions.
Okay, maybe Dr. Jordan want to add up?
The other one is if the frequency of collision increases, is it?
Yes. Okay, I think that's the one. Okay, the frequency of collision. We look at the frequency of collision, and that will actually indicate the reaction is going to be sped up. But again, do remember we have two types. Okay, since Dr. Jordan actually mentioned about this frequency of collision and so on. So there is two types of collision: successful collision and unsuccessful collision. Maybe Dr. Erlin, you want to add up to it? What is meant by successful and unsuccessful collision?
When a successful collision occurs, the reactants collide and react to form products. But when there's an unsuccessful collision, the reactants only collide, but they bounce off, so they do not form products. And this usually happens because there's insufficient energy, which results in an unsuccessful collision.
Okay, thank you, Dr. Lin. So when we mentioned just now, I think I mentioned also this term activation energy. Maybe a lot of us do not know what is activation energy. Can someone actually help to actually explain about what is meant by activation energy?
Activation energy.
So we'll actually let Dr. Dylan to do this. Yeah.
Is the minimum energy that colliding particles must possess for a successful collision to take place. Thank you.
Okay, so the minimum energy required for the reaction, for the reaction to be successful. So maybe Dr. Dylan, you can actually explain, can activation energy be lowered? Because some of the reaction, I think, requires very extreme condition. So it means I assume that they need a very high energy. So is there a way to actually make the energy lower?
No, but there is an alternative pathway.
Which is, can you explain more? Maybe someone else can actually explain more.
We can use catalyst.
Okay, Dr. Ella, can you explain? Later we'll come to Dr. Josh. Yep.
We can use catalysts so that they can react with a different pathway. What the catalyst does is it increases the proportion of particles with lower it increases the proportion of particles that exceed the minimum activation energy needed for a reaction to occur.
Okay. So basically we are telling that this is going to proceed with a different activation energy, or is it going to be lowered? So maybe Dr. Josh want to add up to this?
Technically, the activation energy of the actual reaction, it cannot be changed, but the catalyst itself, it provides an alternative path for the reaction to occur. So for example, we have a reaction that's occurring here, but then with the catalyst, it provides a certain path in which after it happens, the total activation energy is lower than original, and the catalyst that was changed during the middle of the reaction goes back. Because an intermediate was formed, and since the intermediate is unstable, it goes back to its original form.
Okay, thank you.
And thus the total.
Okay.
And thus the total activation energy decreases.
Okay, thank you, Dr. Josh. So maybe we'll actually proceed further. What are the factors that will affect rate of reaction? Maybe Dr. Kenneth can actually help us on this. Maybe after Dr. Kenneth, maybe someone can actually add up to this.
A few factors that affect the rate of reaction are the temperature, the pressure, and the concentration of the product.
Okay, apart from pressure, concentration, and temperature, is there any other factors? Maybe
There
someone wants to
are
say.
Temperature is also a
And
factor.
Okay,
total
hold on,
surface
Dr.
area.
Annabelle. Okay, yes.
The presence of catalyst and total surface area.
Okay, good, good. So, so we can say there are roughly about 5 factors that will affect the rate of reaction. So, namely, temperature, concentration, pressure, catalyst, and one more I missed. What is that?
Surface area.
Total surface area. Okay, thank you, Dr. Ashley. So we have all these factors. So let's actually go one by one. So how concentration affect rate of reaction?
As the concentration increases, there's a greater frequency in collisions. Thus, the frequency of successful collisions increases. Thus, rate of reaction increases.
Okay, so basically the concentration actually increases the successful collisions. So maybe Dr. Michelle, do you want to actually add up to it?
When the concentration increases, the frequency of collision increases, so the rate of reaction also increases.
Okay, so Dr. Michelle, how temperature affects rate of reaction then?
When temperature increase, the kinetic energy of the particle also increase, so the frequent collisions and more successful collisions, which means greater rate of reaction.
Okay, so earlier we have discussed that there are 2 indications, right? One is actually frequency of collision, and another one is going to be the proportion of the particles that having the lower activity, having energy greater than the activation energy. So in this case, like temperature, will it affect both conditions or only will affect one condition? Dr. Raphael, maybe you want to add up to this. So
Unfortunately, sir, my audio cut out.
Let me rephrase the question first so that it's easier for you, Dr. Raphael. Can temperature affect frequency of collision?
Yes, as the temperature will increase, the particles have more energy and can collide more often. This will
Okay.
make the reaction take place much more faster.
Okay, how about the proportion of the particles having the energy that is going to be higher than the activation energy? Is it going to be affected? Or maybe someone else want to help out. Maybe Dr. Lindsay, you want to help out?
Yes, so experiments show that the effect of temperature cannot be totally explained by more frequent collisions. However, but the key factor is that the proportion of successful collisions increase.
Okay, so I think that actually brings us to this concept. I heard about this concept, Maxwell-Boltzmann's curve. So maybe can someone help me about, maybe Dr. Kendrew, can you actually let us know about what is Maxwell-Boltzmann's curve actually means?
It is the distribution of speed for a gas at a certain temperature.
Okay, distribution of, again, we missed you over here. So can you actually explain again?
The distribution of speeds for a gas at a certain temperature.
Speed of gas. I don't think so. Is there anyone who wants to actually argue on this?
The distribution of energies at a given temperature.
Okay, I think that is more suitable in our discussion. This distribution of energy, okay, for I think for every particles, okay, in the system, yes, like for example in the reactant or something like that. Okay, so that is going to be the Maxwell-Boltzmann's distribution. Now, I just want to ask another one more question. I think if we have this Maxwell-Boltzmann's curve, and then I have the here I'm actually showing this curve. I try to understand this curve, and then I fail to understand. Can someone actually help me out to explain how do we supposed to actually look at this curve and actually interpret the data?
So the
We have to look.
Why?
We have to look at the
Okay, just anyone, just one person.
We have to look at the energies
Okay,
as like
Josh.
locations and the number of molecules per energy, like the frequency, the number of molecules per energy. For example, like if we look at this graph and at any given point in the x-axis, it points to a certain molecular energy starting from 0 to like a greater molecular energy. So at the beginning of the graph, the number of molecules with 0 energy is, well, 0. But as you increase, the number of molecules with greater energy also increases until it reaches a peak. From then on, we notice that the number of molecules with greater and greater energy decreases. This is because at a given temperature, the particles in a substance does not have the same energy. Some will have less, some will have more, but generally they will stay in the middle.
Okay, thank you,
So,
Dr. Josh. Thank you, thank you. So how about we have two graphs over here. Can actually someone maybe someone who being very quiet, I think I heard the more you study and then you some of them tend to be very quiet. So we have a lot of experts over here being very quiet over here. Maybe someone who haven't speak yet. Can someone tell me about, okay, there are two graphs over here. How do we interpret? Which one is higher temperature? Which one is lower temperature? Is there any way to predict or interpret this data? Maybe Dr. Kiara?
The one at the higher temperature have lower peak and is more spread out.
Okay, so basically we are telling that the one that is going to be higher temperature is going to be lower peak and is more spread out. What is the reason? Dr. Clienta, what is the reason? Now it's too quiet. Anyone, can someone actually help out in this? Okay, whoever wants to add up. Okay, what is the reason? Why one is actually taller, one is lower? Why? What's the reason, or why it? Yeah.
Because the mean energy of the molecules increase.
Okay. Then what? There is shading over here. What does it represent?
The area under the line represents the number of particles or molecules.
Okay, so it means, does it mean that the total area under the curve is going to be the total number of particles in that system?
No, not necessarily.
What I mean is, like, for example, okay, let me actually show it over here. How about this area, this total? Does it mean the total reactants? Dr. Josh?
It just, for the Boltzmann distribution curves, it only shows us for the substance itself. So it's not technically a reaction. So this is just the substance at a specific temperature.
I think this one, okay, do remember, okay, if we actually, I think this one I have read before as well. If this is going to be total particles having the energy greater than this, so it means that if we actually look at overall, this is going to be the total particles in the system or total reactant. It means total particles, okay? One of the reasons why the graph is going to be a different shape is because the total area must be the same. So that's the thing, when you actually become a bit open over here, it means the total area must be the same. That's why the shape changes. Okay, this is was actually explained by Dr. Gopi before. Okay, I think I still remember. Okay, so anyway, okay, there is still one more question, but I think we lack of time over here. So the last question is going to be, explain the Boltzmann's distribution curve when the catalyst is added. So I have this graph over here. So maybe someone can actually explain about this.
The curve stays the same, however, the activation energy is lowered, hence there is a greater proportion of molecules with sufficient activation energy to react.
Okay, so basically we are telling that, yeah, so overall it's the same reactants, so the number of reactants still remains the same, okay, but the activation energy is going to be lowered, okay, it's going to be an alternative pathway, and because of that, more particles, okay, in comparison to this, they are there, so they can actually react more, okay, so I think this is what I understand. So maybe can someone summarize our live panel discussion so that we can actually end our fruitful session today? Can someone actually, maybe let me actually call Dr. Jordan to actually conclude this session.
Oh, yes. Thank you for attending and goodbye. You are dismissed.
Okay.
What am I supposed to say?
So basically, what do you, how, if we want to summarize rate of reaction, so maybe in 2 sentences or 3 sentences, can you
In
actually
30
summarize?
seconds. It's 30 seconds.
So it's okay. Maybe Dr. Jonathan want to summarize our session today.
We learned about the rate of reaction and what factors affect the rate of reaction and how we can measure it, and also about the Boltzmann distribution graph and how we can interpret it and how it will change based on the changes to the environment of the reaction.
Okay, thank you everyone, okay, for actually spending the time for our live panel discussion today. Okay, see you tomorrow at the same time, same venue. Bye, see you, bye. Thank you guys.
Bye, sir.
Bye, sir.
Thank you, sir.
Thank you, sir.
Bye, sir.